Hi, I'm Mitch Hedlund, co-chair of the 2015 American Packaging Summit and founder and director of Recycle Across America. And I'm meeting with Skylar Tibbits, who is also the director and founder of the Self-Assembly Lab at MIT. And Skylar just finished with an amazing presentation about, for lack of a better term, and I'm sure this is probably going to really minimize what he's working on that's so profound, but it almost seems like behavioral material. I am a very visual person, and it isn't until you shared the videos and some of the imagery to really start to get my mind around the advancements that you're doing. But can you just give us a brief summary? And you're so good at being able to do it in a very comprehensive way, but where things are going with your developments and your research so far.
Yeah, so we are interested in finding ways to program materials to either build themselves or transform, physically transform in radical ways. And that really is from a lineage of the software revolution to the hardware revolution, and now there's happening a materials revolution from biology to chemistry. We're at very macro scale, so we make big stuff. We want them to transform in new ways, whether that's adapt to the user or adapt to environments or new manufacturing applications.
And relevant to the conference that we're at right now, do you see this being a future of packaging technology, creating self-assembling packaging basically with this smart material?
Yeah, we're extremely fortunate. Lots of companies have come to us based on what we've shown. We have these abstract, crazy things transforming, and then they say, can we apply this to packaging? Can we apply it to furniture, etc.? And packaging is one that comes up over and over and over again. The interest in smarter packaging, whether that is to reduce waste, whether it's to reduce cost or materials, to make packaging more adapting so that it can adapt to the product inside, the fluctuating environments around, adapt to impact so that it protects the product better, or recyclability for dissolving, separating, removing the material after it's on the shelf, or maybe lastly, as the product gets there, how does it assemble itself on the other side? So the product is the package. It transforms into another dimension when you get it.
Right, really remarkable to even think that something can take a new form almost simultaneously or on its own. And can you just remind us what the materials are? You mentioned 3 different types of materials that have this ability right now.
Yeah, our broad vision is to be able to program any material with any industrial process. So far, we originally started with printed materials. So we 3D print things with various polymers. We call that 4D printing because we get them to transform over time. More recently, we showed that we can do that with more traditional materials like carbon fiber and other composites and fiberglasses and things like that, wood and textiles. We're now looking at rubbers, and we're interested in metals, and there's lots of different traditional materials. We make them active by combining them in different ways and then subjecting them to energy, heat, moisture, light, electricity, etc.
And when these materials react to different temperatures or moisture or humidity, is there kinks that still need to be worked out to make sure that under all conditions, once this technology is brought into manufacturing of let's say packaging and products, are there some kinks that still need to be worked out to make sure that things don't change based on environmental changes for the packaging?
So, everything transforms anyway. Like if you heat something enough, it's going to burn, or if you heat something enough, it'll melt, or if you drop a bunch of stuff, it'll create a pile. The challenge is how to make it useful and not destructive, right? So the way that we do that is to think very carefully about what is the energy, the amount of energy, and the type of energy that you want to activate it with, and then think about what do you want it to do that's useful. You don't want it to just make some arbitrary thing. You want it to go from this shape to that shape, or you want it to become more rigid under impact or more breathable. So you try to find the mechanisms to do that, and then you think about when and why does it do that. I want it to do that only when temperature goes above a certain amount, or I want it to do that only when there's this much moisture in the environment. And you try to think about energies that are only under those conditions and would never happen arbitrarily. So temperature has to be above a dangerous threshold, or altitude has to be a certain level, and therefore you can avoid mistakes of transformation.
Right.
You can also start to combine energy, so only if this plus this does it transform, and that starts to build in like protection mechanisms.
Well, I think it's really interesting because it's taking traditional materials that sometimes react to conditions, which usually leads to a problem, and instead your group is finding ways to take what would be a reaction that creates a problem, but instead controlling the reaction to be the solution. The other thing that we want to focus on, and this is the lens that I continuously look through, is the sustainability element. And you touched on that a little bit in the beginning of our interview, but I am curious to know, is that being designed into this innovation? Is that part of your continuous consciousness as you're developing these technologies?
Certainly we're interested in that, and that's maybe one of the goals. I wouldn't say we start out by saying, what's the most sustainable thing we can do? We never start by solving a problem. We always start by pushing the boundaries of what we think is possible. Like, is it possible? If not, why not? Let's find a way to make it happen. What's the craziest thing we can possibly do? How far can we push our minds and our materials? We think about those kind of crazy things, and then through that you find amazing and relevant applications, which almost always are more sustainable, because we often use energies that we forget about. Right. So we don't use fuel or batteries or electricity often. We use moisture, sound, sunlight, other types of light, temperature, and all of these are things we don't take advantage of. We've forgotten about. We think there's only one type of energy that makes things useful, by plugging something into the wall or throwing a battery on it. Often they're everyday materials. So, that makes it far cheaper, easier to use, easier to put together, and more highly dynamic, which means that it's, we often run into this thing where we see that it's over-engineered. So meaning over-engineered to be super rigid and more material so that it's super redundant. And what we want is to try to find super lean, minimal materials that transform when needed.
Right.
And therefore you can cut out a lot of the waste. And then there's a whole vision of disassembly for recyclability. So it's sort of a byproduct that you find, by thinking differently, you find all these opportunities for sustainability.
Cost reduction. What do you see as being, in the future, a potential cost reduction element of this? Is it reducing labor? Mm-hmm. Is that something that can be offset somehow if there's job loss, mm-hmm. if things are building themselves and so forth? What does that mean to the economy, and what does that mean to the economics of producing?
Yeah, that's one of the questions we get most often is, well, I guess there's two. One is what happens if it goes out of control, and two, what happens if you replace the jobs. And I think there's a longer answer to try to keep it short. One is that anytime there's new technology, the main fear is how is it going to either go out of control or replace jobs. So the telephone to the printing press to the computer to the train to the car, every single one, those two fears were there. And it's neither of them are true. That new technologies create jobs, mm-hmm. and new technologies work with humans. And our goal is exactly the same, that it's not about replacing humans or machines, it's about collaboration. And we basically look at it as there's three factors. There's machines, robots, etc. And they're great at repeatability, they don't ever get tired, precision, all those kind of things. Humans are great at creativity, high-level thinking, abstract thinking, management, goal direction, etc. And materials are great at physics. Materials respond to energy. Materials can have programs. They can sense things. They can give information. And it's really those three communicating with one another, which makes a more efficient and totally radical relationship.
So it's really an evolution. It doesn't eliminate. Yeah. It's just a broader process, maybe, broader opportunity. And then my final question is, what's the first practical application that you see this being used for?
Yeah, as I said, we're working with a lot of different industries, and there's different, let's say there's different cycles. Every industry has its opportunities and challenges and visions for the future, and some of the near-term things are industries where it has this right mix to foster innovation. So some of those capabilities are you need to be able to work quickly. You need to have performance demands or demands that are making you think differently, whether that's energy and sustainability, or it's like athlete performance or efficiency and like cars and planes and all those kind of things. The regulation environment has to be ripe, so it's safe but also fosters innovation, and there needs to be like competitive marketplace and marketing, and a great benefit for the company cost-wise, that they want to both save and make more money based on performance and increase in technology. And so, sportswear and furniture and even aviation or the medical space, some of those have crazy regulations, but they're innovating constantly, and they can move quickly and they can introduce things. And so those are some of the markets that we're working in, and with great partners, we're working on new technologies there. And the Airbus example that I talked about today is one that we're actively working on. It's in wind tunnel testing in Toulouse, and then hopefully flight testing, and then certification and stuff. But there's many different spaces, and it has to have just the right amount of those elements to be able to move quickly.
It's so fascinating. Medical technology, do you see this a big application in that?
Yeah, there's many applications, from orthodontics to stents to compression garments and devices to go on the exterior of the body. And medical is an interesting space. There's a lot of regulation, but you can move quickly as well, and there's performance requirements.
Fabulous. Really, just so remarkable. I'm completely compelled by this subject, and I think it's going to be interesting to see what happens in 5 or 10 years, or maybe less, sooner. Things are on this trajectory, but very cool to see how this can apply to the packaging industry and product industry relative to this event. So thank you, Skylar. Thank you so much. What a pleasure.